In this video, we're going to learn how to calculate the packing density or packing fraction of the diamond crystal. In case those concepts are not super familiar already, I'm first going to explain what the packing density is, what it means. Then I'm going to explain what the diamond crystal is and an easy way to imagine it. And then we're actually going to calculate the packing density. If you take a look at the unit cell of any crystal structure, like for example this face-centered cubic right here, you can see that there are gaps in between the atoms. So the volume of this cube is only partly taken up by atoms. And the packing density, or packing fraction, which is the exact same thing, just another word for it, is the percentage of this cube volume that is taken up by atoms. So the closer those atoms are smashed together, or the closer packed they are, as you would usually say in solid state physics, the higher the packing density. Now, if you just look up the term diamond crystal structure, you will most likely find something like this, which looks pretty complicated, especially compared to simpler crystals like the FCC, because you have those atoms in the middle that have those weird distances from one another that don't really seem to follow any pattern. But there is a really simple way to define the diamond cubic, because this diamond cubic right here is nothing but two face-centered cubics of edge length A, so this right here would be A, offset by 1/4 of an edge length in each direction. What that means is the following. We have one FCC crystal here and one FCC crystal here. The face-centered cubic has one atom in each corner and one atom in each of the faces. Now we're going to take this one, push it into the first one, and we're going to offset it slightly by about 1/4 of an edge length in each direction. That means if this corner right here is the origin, so coordinates 0, 0, 0, and those cubes have edge length A, then the coordinate of the lower bottom left corner of the second cube we pushed into this one is going to be 1/4, 1/4, 1/4. So the green cube is A/4 units further to the right than the blue cube, A/4 units further back, as well as A/4 units higher. If we now focus on the blue unit cell, we can see that some of the atoms from the green FCC crystal are outside of the blue cube, but some of the green atoms, namely the one in the floor, the front lower left corner, the one in the front wall, and the one in the left wall, are now inside this blue cube. So this unit cell with the blue corners, including the atoms that we just pushed into it, is exactly this right here. Now, in order to calculate the packing fraction of this diamond crystal we have just created, I'm just going to call it PF, we have to divide the volume that is taken up by the atoms inside of the cell by the volume of the entire cell itself. We get the total volume of the atoms by multiplying the volume of one atom times the number of atoms inside the unit cell, and that's what we're going to divide by the volume of the unit cell itself. Since in this model we act as if the atoms are solid spheres with a radius of r, the volume of one atom is simply going to be the volume of a circle with radius r. So V atom is going to be 4/3 pi r to the power of 3. Next, we need the total number of atoms contained within the unit cell. Let's just call that n. We don't really need to calculate this n, we can simply count it, and we're going to do so in a second. And since our unit cell has edge length A, and it's a cube, the volume of the unit cell is simply going to be a to the power of 3. Now let us first find n. N is the number of atoms contained within the unit cell. So we need to take into account the ones that were already part of the FCC crystal in the first place, as well as the ones we pushed into it. Our initial blue FCC crystal has an atom in each corner, but those corner atoms contribute only 1/8 of the atomic volume each. So we have 8 of those times 1/8, which is 1. Then we have in this FCC unit cell 1/2 of an atom in each of the cube's edges. A cube has 6 edges, and 6 halves make 3. So the initial blue FCC crystal contributes 4 atoms in total to the diamond structure. However, we pushed 4 additional ones into it, from the green FCC crystal. So we have to take those into account as well. 1 plus 3 plus 4. So n is going to be 8. In order for this result to become a number and not some weird expression with r and a, we need to find a way to express a in terms of r so we can then cancel the r. And for that, it's really important to recall that the smallest possible distance two atoms within a lattice can have from each other is touching distance. And since we assume the atoms to be solid spheres, if you have two solid spheres of equal size that touch each other, the distance between their centers is twice the radius, so 2r. Now, since these two FCC crystals, which we use to build the diamond cubic, are only slightly offset from each other, the shortest distance is this one right here. And how do we find this distance? Well, if we know the coordinates of both points, we can treat this as a vector from the origin to the coordinates a over 4, a over 4, a over 4. And from our model, we know that the shortest distance equals 2r. So 2r is this distance right here. And how do you find the length of a vector? Well, using the absolute value. So 2r is the absolute value of that vector. So we're going to have this super long square root containing a over 4 squared plus a over 4 squared plus a over 4 squared. That results in square root of 3 over 4 times a. If we now take this equation, 2r equals square root of 3 over 4 times a, and solve it for a, we get a equals 8r over square root of 3. So now we manage to express a in terms of r, and if we plug it into this formula, we can cancel the radius, and we're left with just a number. So let's plug it in. Packing fraction equals the volume of our atom, which is 4 over 3 pi r to the power of 3, times the total number of atoms inside our diamond cubic unit cell, which is 8, because we found n to be 8, divided by a to the power of 3, and we found a to be 8r over square root of 3 to the power of 3. Since we have r cubed up here and r cubed up here, we can completely cancel those. So now the only thing left to do is putting the remaining values into a calculator, which gives us 0.34 or 34%. That is the packing fraction of the diamond crystal, and it means that only 34% of the total volume of this diamond cubic unit cell is taken up by atoms. I really hope you found this video helpful. If yes, consider sharing it with a fellow student who might also benefit from it, or subscribing to the channel. Thank you so much for watching, and see you in the next one.